All right. Last lecture, we looked at an amplifier, a three-stage amplifier. And one of the things that we noticed is that we had a three-stage amplifier that it was open loop, and we simplified it, and we saw that it had, the way we had designed it and simplified it with three capacitors, it had three poles. And then when we put it in feedback, we saw that as we increased the amount of feedback, it went from a point where the response went from, let's say, the step response went from something that was kind of pretty straightforward to something that started ringing and ringing more. And at some point, once we applied more feedback, it basically became, instead of being an exponentially decaying sinusoid, it became an exponentially growing sinusoid, and it became unstable and all sorts of things. And the other thing that we saw is that also we noticed that when we introduced some resistors in series with two of the capacitors, in other words, when we introduced two zeros, for the set of values that we had, that amplifier was still producing a lot of, if you broke the loop and you fed something in, something came back that was larger and in phase, a sinusoid more specifically. We put a sinusoidal input in, and the sinusoidal output came back around the loop, and we calculated the loop gain, which was exactly in phase and larger at two frequencies, but still the system did not oscillate. It was actually a stable system, which was kind of a counterintuitive thing. So it was supposed to be at least a counterintuitive thing, a little bit. And we said, okay, well, what's happening? So today we are going to discuss, do the analytical way of thinking about these things and see how we can find out what kind of solution we have. If you remember so what is the basic premise of all of this thing is that we calculated this parameter loop gain, right? And we saw that the denominator of the closed loop transfer function has this term in it, 1 plus T of S. So if you want to find the loops, the roots, the poles of the denominator, the poles of the closed loop transfer function, we have to solve this equation. This was the equation we tried to solve. And we saw that this is equivalent to saying that basically the determinant of the Y matrix is 0. So the solutions to this and the solution to this are both the poles of the closed loop transfer function, right? And we wanted to evaluate them. And to know whether or not a system is stable or not, we have to know whether or not the poles of this transfer function are in the left half plane or right half plane. And what it is that it takes one crazy guy basically to destroy everything, meaning that it takes one right half plane pole to make the system unstable. It doesn't matter if you have 1,000 left half plane poles, right? Just one right half plane pole will make the system unstable. So we are trying to determine if we have right half plane poles, and the other question is that how many, if we could determine that, if we wanted to do that. So today we'll discuss methods of doing that. There are several different methods. Some of them are analytical, as we will discuss, and there are some numerical methods, and some of these analytical, and some of them are graphical. And we'll talk about all of them and see where they come from and how they work. So if you remember from the example that we talked about last time, we could calculate actually the polynomial that described the denominator polynomial, right, in terms of S. So we had a third order polynomial in both cases, the two variations of the example that we looked at, and I wrote them down in some numerical values, right? So I don't remember, 6.35 S cubed plus whatever, S squared plus something. So if you have a polynomial of that sort, the question is that, and we saw that by looking just at the coefficient, the fact that the coefficients were all positive did not necessarily indicate that all the roots were in the left half plane, right? Meaning that it didn't necessarily mean that all the roots are in have negative real values. So how do we determine that? So there's an old mathematical method, and you're probably most of you are familiar with. The question is that if you have a polynomial, you have a polynomial in S, which is of the form an s to the n plus an minus 1 s to the n minus 1 all the way to a1 s plus a0. How do you know whether or not it has any roots in the right half plane? And this method is an old method developed by a couple mathematicians named Routh-Hurwitz method. So this is the most basic method, really. I mean, the most straightforward. So it's a mathematical algebraic method, right? It's it's an algorithm essentially, really, for evaluating these things. And what it says is that just take these coefficients and start from the highest order coefficient, let's say an, and write every other one in the first row. So you get an minus 2, an minus 4, all the way up. And then you get an minus 1. Again, the other ones are written here, all the way down. And what you do, then the process is like this. And we don't prove this here, but if you are interested, I can give you a reference for the proof. I mean, and you look it up online, Routh-Hurwitz method, you can find it. So it says, basically, you calculate the product of these two and subtract from it the product of these two and divide it by this coefficient and put it here. So this is basically, let's call this Bn. So the way we described it, Bn is an minus 1, an minus 2 times an times times an minus 3 divided by an minus 1. So that's Bn. And then the next one over, I'm going to show it with a different color to just be clean. So so that we can call it Bn or B1. Let's call this B1. The name doesn't matter really. B1. So let's call this B3. So B3 is the product of these two. Now look at it. These two minus the product of these two divided by this guy again. So B3 would be an minus 1, an minus 4 minus an minus 5 divided by an minus 1. And so on and so forth. So the next one over would be this times that minus this times that one, the next one over, divided by this, and so on and so forth. You form another row. And then you repeat the process, meaning that next time over, you do it for the last two rows. The new row that you generated and this one. So you basically now repeat it here. So you say, this time you say, it's this times this minus this times that divided by Bn. So basically, if you have C1 would be B1 an minus 3 minus an minus 1 B3 divided by B1. Okay? You can just say divide by. And then so you can have it. I'm just going to put the same color code here to show that graphic visually. And you keep doing this till you run to 0, till you basically all the coefficients become 0. And what you can tell from this is that the number of sign changes, sign changes in the first column is equal to the number of right half plane poles of this root. So you see how many times this changes sign? That's the number of right half plane poles that you have. If it doesn't change sign, it means that you don't have a right half plane. Right? And this is a pretty straightforward algorithm to follow. I'll give you a couple examples. And there's nothing magical about how you apply it. It's a pretty straightforward thing. So if you have a polynomial numerically, you can always apply this method. You can even write a little piece of program to actually do it for you if you wanted to do it this way. There are other ways to factor a polynomial numerically, but you can do it. So here are a couple examples, quick examples. Example number 1 is the polynomial being s to the 4 plus 10s cubed plus 35s squared plus 50s plus 24, right? So how do we do it? We write these numbers in that order. So we start doing this. So we start from the highest order term. So we get 1, right, here. And then the next one over is 35. Next one over is 24, right? And then this, we start with the remaining ones, the odd or even, if you will, 10 and 50. And if you leave it open, it basically means it's 0. You can write it 0 explicitly or not. And then when you do that, OK, so now what the first step is. Look at the first step. The first step is 10 times 35 minus 50 times 1. So 350 minus 50, 300 divided by 10, 30. Right? Then you do this one. It's 10 times 24 minus 0 times 1. So it's basically 10 times 24 divided by 10, which is just 24. And these are zeros now. So and then you do the same thing here. So you get 30 times 50 minus 10 times 24 divided by 30. So that's basically 1,500 minus 240, right? So that's 1,260 divided by 30. It's 126 divided by 3. It's 42, right? And then these are both zeros. So if you do this multiply by this minus this multiply by that is 0 minus 0. It's 0. So it's 0. And then the last one is 42 times 24 minus 30 times 0. So 42 divided times 24 divided by 42. So it's going to be 24. And the next one over is going to be 0 because both of these are 0. So basically it's going to be 0. So how many sign changes did we have in the first column? None. So if this polynomial was the denominator of your transfer function, it means that it has no right half plane poles. So that's an example of a stable. If this were the denominator, that would be a stable transfer system. Bibo stable, meaning bounded input, bounded output. If you apply bounded input to it, you will get a bounded output. Okay? So now, let's do another example. So this is one example. And then example 2, just simple example. Let's pick this one. So s cubed plus s squared plus 4s plus 30. And if you pick this example, what do we have? What are the coefficients? So let's write them. So we start from the highest order one. It's 1. The next one over is 4. This one is 1. And next one over is 30. Okay? So 1 times 4 minus 1 times 30. 30 is basically 4 minus 30 is negative 26. And then the next one over is this times that minus 0, because this one is 0. Divided by 26, you get 30. Right? So how many sign changes did we see? Did we observe? 2, right? So how many poles does it say? How many right half plane poles does it say it has? 2. Right? Now, you look at something like this, it's not obvious just by looking at it in general that you have right half plane poles, right? Because all the coefficients are positive and you can say, but in fact I can tell you what the factorization of this thing actually is, right? So if you factorize, this was constructed to have a certain factorization, right? So it's basically, this is s plus 3 times s minus 1 squared plus 3 squared, which you can write as s plus 3 times s minus 1 minus j3 times s minus 1 plus j3, or 3j. So you can see that what you have is, if you look at the pole 0 constellation, right, you have a pole at negative 3 in the left half plane, and you have 2 poles with a real value of 1 and imaginary values of plus and minus 3. So this is 1, this is 3, j, in the S plane, real and imaginary. So you have a pair of right half plane poles in this case. So you should not be fooled by the fact that these coefficients are all positive. Because you can get in a situation where you have poles that have positive right half, real values. Okay, so Routh-Hurwitz is an interesting thing, more of a historical thing, and it can be useful in certain applications. But a lot of times you may not actually have the polynomial, the denominator, in that form. Sometimes it may be parametric. Sometimes it may not even, you may not even have that. You may have a measurement of a system, right? What you can measure things like Bode plots, right? You can apply a sinusoid, and you can change the frequency of the sinusoid to the input. And as you change the frequency of the sinusoid, the amplitude and phase of what comes out changes. And when that happens, basically you are looking at, you can plot that versus frequency, and that's Bode plot, right? You can plot the magnitude of the ratio of the output to the input, and you can plot the phase of the output sinusoid to the input sinusoid versus frequency, and you have those kind of things. The question is that, can you do some sort of analysis based on that? Can you do some sort of a stability analysis? And that's basically what leads us to the Nyquist criterion. Okay? So we are going to develop, but the objective is still the same. The objective is try to determine the roots of 1 plus T of S. Right? Because those are the parameters that we are interested in. Those are the poles of the open loop transfer function. And the question is, what can we do to determine these accurately? So for that, we are going to develop this. And the derivation of the Nyquist criterion that we'll do here is a little bit different from what you see typically in most textbooks, which is they basically go to the residue, complex residues and all those things, and you can calculate it from that. We kind of like arrive at it implicitly in the derivation. So we actually kind of like derive the Cauchy principle directly, simply, and then we apply it in practice. So you will see how it works. So that way, at least you can see the process. So imagine that you have a function f of s, right? So you have an s, and then you have a function of this s. Both of them are complex. So this is a complex quantity, and this is also a complex function of a complex variable. Right? So if you think about it, if you look at s, so s is in this plane. So right, this is the real of s, and this is the imaginary part of s. And now let's imagine that you also look at the plane where you evaluate the function f of s. So this is the real of f of s, and this is the imaginary part of the f of s, both being complex quantities, right? The complex variable and a complex function. So now if I have let's say if s changes its value, let's say more specifically, s traverses a closed contour. So let's say it takes a trajectory, it has a path that it traverses. So this is the value of s, right? So I take the s and change its values as it goes through here. What would happen on that side? What would you imagine that would happen to the general function f of s? There's one thing you can say about it, really, right? The only thing that you can say is that this is going to be a closed contour. Right? Because value of s comes back to the original value. So if f is a function, if it's a single, which means that it's single valued for a given s, so it has to come back to that value. It's a closed contour. I mean, it may kind of go on itself multiple times. It may do all sorts of crazy things, but it has to be a closed trajectory. So I'll show it like this. Some closed trajectory, right? We can call this C1, and we call this C2. So there's a closed trajectory here and a closed trajectory there. So now let's imagine a couple of different scenarios. Imagine the first scenario where you have let's say a 0 and maybe a couple of poles here, complex poles here. Just as an example to see what happens. The question is, what is the phase and amplitude of phase and magnitude of this f of s? Excuse me. So what we know is that f of s is a complex function, right? So, and if assuming that it's a polynomial function, well, it's a rational function, we can write it in this form. So we can write it as a s minus z1, s minus z2, s minus zm, and then you have s minus p1, s minus p2, all the way to s minus pn. Right? If it was a rational, if that function is a rational function, we can write it in this form. Now, if you can write it in this form, what is its phase and amplitude? You can also write this as magnitude of A, magnitude of s minus z1, magnitude of s minus z2. Because if you think about these individual components are vectors, right? What is s? Can we look, for example, look, let's say this is z1. What is, and this is s, for the sake of argument. Where is the vector s minus z1? It's this vector, right? So this vector, the one I'm drawing, is s minus z1, right? Do you agree? So that's vector s minus z1. And if there were other zeros, it would be s minus z2, et cetera, et cetera. So you can basically write them as magnitude of these vectors. And then the denominator, the same deal. So you have s minus p1. So what's s minus p1? It's this vector, or p2. So this is let's say this is p1 and this is p2. All right? So it's these vectors. So you're looking at the magnitude of those things, s minus p1, s minus p2, all the way to s minus pn, times, now the phase components of these things, right? So the phases of each one of them, the phase of the first component is e to the j, what I show it as phase angle of s minus z1, right? That's the phase angle. And the second one has a phase angle of e to the j, phase angle of s minus z2, and so on and so forth. And then the denominator, the same deal, e to the j, phase angle of s minus p1, and e to the j, phase angle of s to minus p2, all the way up. And of course, what you can see here, or maybe I can write it, continue down here, is that it's this part that's the magnitude of the whole thing, right? So this you can call it as magnitude of f of s, times the total phase, which is what? The total phase of this thing, which is going to be theta 1 plus theta 2, right? All the way to theta m, which is the phases of the angles of these vectors, right? So, for example, this is theta 1. And then the angles associated with the minus, the angles associated with the poles, call them phi 1, phi 2, all the way to phi n, right? And those are, for example, here. So this is, for example, phi 1, and this is phi 2. Agreed? So do you agree that the total phase angle, that the f, so this is, for example, vector f of s. So this is f of s for any given s. And this is the magnitude of f of the vector has a magnitude of f. And this angle, this is the phase of f of s, which is this quantity. So that phase angle for that value of that function, when you put an s in, the value that the function assumes will have this magnitude and phase. And this is its phase, right? Which is basically says all of these blue phases minus all the red phases. Do you agree? So now the question is, what happens if I don't have any poles and zeros inside this contour? If I pick a contour that doesn't have any poles and zeros inside, what would you get? What would happen to the total phase? Well, think about it this way, right? So this is a, so let's say this represents the vector this guy. So for each one of these, let's assume that the blue one, right? If that 0 is outside this contour, right? As this S traverses the trajectory of this thing, what happens is that this phase goes up, and then it goes down, and then it goes down, and it comes back up, and it goes back there, right? So for one closed trajectory, you do some up and down, but you don't do a twist, a full turn, right? So for example, if I had a rubber band attached to the tail of this thing, right? This rubber band would not have a twist at the end of this process. You go bend one way and comes back, but it's going to be back to where it was. It won't end up with a full twist or multiple twists, right? Same thing with the poles, the phase angle that they introduce, each one of them. And we know the total phase angle is the sum of these minus the sum of these. So what does that tell us about this contour? Simple, well, does it have to be a simple loop? Because it can actually do multiple times. I mean, if it went two turns, right? It can still happen, right? I can make this funny looking, so I can basically make this go up and come down and up and down. But there's one thing that actually would not happen if these things are outside. There's nothing inside of it, yes?
It would enclose the origin.
It would not enclose the origin. Because if you think about it, the angle of this guy, if it doesn't enclose the origin, would not end up with a twist. That rubber band would not end up with a twist in it, right? Because it will go up and down and up and down. It may actually go all the way around, right? So you can have some sort of funny looking thing. I'm just going to draw something here. It can do this. But if I'm sitting at the origin, at the end of the day, if that's my contour, I will not end up with a twist. Right? Because it will go back, but then it comes back. Just that is cancelled at the end of the trajectory. Right? So what it tells you is that you go up and down, but you will not be enclosed. However, so now let's think about another example. So now let's say you have a pair of poles here in addition. Now, let's start with a simple thing. Let's say you have one pole. Just to make things simple, and then we'll go to the pair. So if I had one pole inside, what happens to the phase of this guy as I'm traversing, right? So I'm going around and coming there, and then I will end up with a twist in that rubber band, right? With one twist. And since the total phase of this thing is the sum of all these phases, well, these with positive sign, these with negative signs, right? So I will, in this scenario, if this was my pole 0 constellation, I had these 3 poles and that's 0, I will end up, this guy will have to encircle the origin how many times? Once. And in what direction? Clockwise or counterclockwise? Let's say this contour is going clockwise. If this was a pole. Counterclockwise, right? Because of this minus sign. So if I had a single pole, this would be something like this. I mean, exact shape of it, I don't know what the exact shape of it is. All I know is that it will enclose the origin, and it will go counterclockwise. Net counterclockwise. It may actually, so it may in fact do this, right? So for a little while it's going clockwise, but it means that the net twist that you will end up with in that rubber band is going to be a negative 2 pi. Negative because we defined the clockwise and counterclockwise the opposite of the classical direction, but 2 pi counterclockwise. Okay, let's make it that way. So, all right, so that's what. And if I had a 0 there, so now if I had 2 poles, what can you say? If I had the 2 pole scenario, let's say. It has to encircle the origin twice. So it means that at the end of the process, you have to end up with 4 pi counterclockwise twist, meaning something that could be like this. So by the end of the process, this has gone 1 and 2 twists. So from this, what we can tell is basically something important and relatively straightforward, is that the number, and if I had zeros in there, what would happen? So let's say now I had a 0 there too, a right half plane zeros. What would you end up with? How many turns?
We only encircle once.
Encircle once and counterclockwise, right? Because this one would produce a phase that would be counter to that. So what it tells us really is something that's quite simple, right? It says that the number of the encirclements of the origin in this plot, right? So if we had this thing, our plot would look something, well, let me just do a different plot. Our plot would look something like this. So the number of times that the origin is encircled, so let me just write this down explicitly. The number of origin encirclements is equal to the number of zeros minus the number of poles inside the contour. Okay? It's a very simple, straightforward thing, right? I mean, now that we can see it. So the question is, can we use this to determine something meaningful? So one of the things that, what were we trying to solve? Well, we are trying to find out if 1 plus the loop gain equals 0 has poles on the right half plane, right? So what we need to do is to define a contour that allows us to understand what's happening with that, right? So what is the contour that we need to define? So if this is the S-plane, the contour 1 that we can choose for something like this is this line. We can go basically all the way to infinity and then come back. So basically, we encircle the entire right half plane. If we encircle the entire right half plane, then if there's anything in there, it will pop. Well, kind of, right? The problem is that you may say, what if I have a pole and a 0? It would not show anything. I mean, it would not have a full encirclement. Let's see what we can do about that. So if you have something like this, and then it ends up, for example, with a plot of 1 plus 1 plus t of s, being something like this. Let's say you end up with a plot that looks like this. A contour looks like that. So what does that tell you? What can you tell from just by looking at that? What can you tell? Equal number of right half plane poles and zeros. Yes, correct. So the number of right half plane poles and zeros are equal. But we don't know if it's 5, if it's 5 poles and 5 zeros, or 0 zeros, 0 right half plane zeros, and 0 right half plane poles. But based on that by itself. Okay? So this is basically obviously the real and imaginary part of this quantity. 1 plus the loop gain. Sorry? Is that flipped? Yes, it is flipped. Thank you. Somehow it wants to come back. Okay, now I got it right, I guess. 2 attempts. A 0 and pole were canceling each other. Okay, so now here's the key part, the key insight. The key insight is that if you actually look at the parameter we are trying to evaluate, which is 1 plus t of s, 1 plus the loop gain, and the loop gain can have a numerator and a denominator if it's a rational function. You can write it as d of s plus n of s divided by d of s. Okay? So now one of the things that you can tell is that the roots, the poles, so we know the poles of T of S are the same as poles of 1 plus T of S. Right? So what does it tell you? It tells you that if your loop gain itself is stable, right? If the loop gain itself are stable, you will not have right half plane poles in this or that. So all you're evaluating is that the number, so what we know, the number of encirclements is the number of right half plane zeros minus the number of right half plane poles. So this is the number of encirclements of the origin. Now if you don't have any right half plane poles, so simply what we get is the number of right half plane zeros of this quantity, right? But that's what we are looking for. We're looking for the roots of this quantity, right? We are trying to find the roots of this quantity. So the number of right half plane zeros is the number of right half plane roots of that 1 plus T of S. Agreed? Which are the poles of the closed loop transfer function. Because the closed loop transfer function has this in the denominator. Right? It's 1 plus AF, 1 plus T in the denominator. So the roots of this quantity are the zeros of this quantity, and then the zeros of this quantity are the only right half plane thing you get if you start off with a loop gain that's stable itself. So if your open loop system is stable, so you have to start with a stable open. When you open the loop, if the system is stable, then when you close the loop, the number of right half plane poles that you get for this are the number of encirclements of the origin of 1 plus the T of S. Does that make sense? So that leads to a criterion. So what can happen is that because you have the 1 plus T of S, you can shift everything, and instead of dealing with the origin, you can deal with the point of -1, and just deal directly with T of S. So that's what Nyquist criterion is. Nyquist criterion is this. It says, look at the real and imaginary value of T of S, not 1 plus T of S, and look at the number of encirclements of point -1. So everything is the same as before, as this picture, except for the fact that everything is shifted by 1 in the x direction. Right? So the role that the origin was playing is now played by this point -1. Should use a different symbol, -1. So it says, plot the real and imaginary value of the T of S, which is the thing that we know how to calculate. We know how to evaluate, right? We went through all this trouble of defining unilateral, bilateral T of S, right? To be able to do this kind of things. So, for example, you may get something that looks like this. So if you get something like that, a trajectory, as you traverse through what pathway? What is the pathway you're traversing? Remember, the contour you picked is basically for S being negative j omega, for omega going to negative infinity, or to j omega for negative going to j omega, where omega goes to positive infinity. So you're sweeping omega from negative infinity to positive infinity, just the imaginary part of it. But what is the imaginary part giving you? The imaginary part is this kind of like the sine and cosine part, right? As you traverse this, if you think about starting from 0, let's say, from 0 to plus infinity. So let's say you're here at 0. So this is omega being 0. And this is omega. So at this point, omega has gone to plus infinity. So this is the upper half of this thing, right? Where do you usually have this quantity, this kind of measurement? Bode plot. That's what you do in a Bode plot. The Bode plot essentially is the magnitude and phase of this quantity. So this is the magnitude of t of j omega, right? And this phase is the phase of t of j omega. Right? So if you have the Bode plot somehow, either through a measurement or calculation or something like that, you just take the Bode plot and do a polar plot of the Bode plot. And you look at how it behaves with respect to point -1. And that gives you a sense of whether or not you're stable. Now, for systems that have real coefficients, the upper and lower part of this thing have to be the same, right? Because of the symmetry of the poles zero constellation with respect to the with respect to the real axis, right? Because the poles or zeros have to come in complex conjugate pairs. Because if you have a polynomial, right, with real coefficients, if you factor it, you can factor it in terms of first and second order polynomials with real coefficients, which means that the second order polynomial with real coefficients will generate a pair of complex conjugate poles or zeros, depending on whether or not they're in the numerator and denominator. So all you really need to look at is half of this, starting from 0 to infinity. Because the other half would be symmetrical, and that's why I kind of drew it symmetrically like this. So you can actually, a lot of times when you do Nyquist analysis, you don't even show the second part of it. So you just basically ignore this part, which is the part from negative infinity to 0. And you look at the encirclements of that. But if you have questions about how many times they encircle, think about the other half of the graph and see what it does. So now, based on our criterion, the Nyquist criterion, is this stable? Is this system stable? Yes, right? So we are going to do a bunch of other things that I'll ask you if they're stable or unstable. So let's say this is point -1. What if our trajectory or Nyquist plot looked like this? Is this stable or unstable? Well, think about the other half, the mirror image with respect to the real axis. So the mirror image looks like this, right? Well, that would be a tough one to replicate, I guess. So did we encircle point -1? How many times did we encircle it? How many times? Well, if you're in doubt, see if you draw a line straight out of that to infinity, how many times would you cross? So how many twists will you end up with? How many 2 pi's? How many full twists? 2, right? So that means that you have a system like that has 2 right half-plane poles. So you have 2 right half-plane poles because you encircled it really twice with that picture. So you have to be careful when you look at these pictures, because if you ignore the other half of it, you may not see the other part of the plot. So that's unstable, meaning that you can get unbounded output with an bounded input. You can hit it with something finite, and then it will eventually can grow to like maybe exponentially grow, or sinusoidally, a sinusoid that grows exponentially to infinity. So how about some more examples? Let's say, so now we can actually make more fun examples, because now that we have the basic principles. Okay, so how about this? Let's say you start from here, you go here, and then you go there. Is this stable or unstable? Stable. How many people say it's stable? How many people say it's unstable? Okay. Well, let's look at the other half of the contour, I guess. So really, the other half starts from here, if you're in doubt. So this is the trajectory, right? So how many full twists would you end up with? Well, if you're in doubt, let's start from, I don't know. So this is negative infinity path, right? Well, I don't need something this way. Let's say this, right? Okay. I'm going through the negative infinity. Starting from negative infinity, going here, going down, coming back up, going down, coming back up. There. How many twists did we get total? 0, right? Net 0. So according to the Nyquist criterion, this is stable. Because we didn't have full twists. So, but look at this plot. What is the Bode plot of this thing like? I'm going to just draw that part of it, obviously. Qualitatively, right? So you have something that has some gain, and then gain eventually drops to 0, right? Because eventually at infinity is going to 0. And then if you look at its phase, so let's say this is negative 180. The phase is going down below 180, but it's coming back up before you hit unity, because this is the unity circle, right? So the phase goes beyond 180 when the gain is greater than 1. Let's say this is 1 or 0 dB. Right? And then it goes back up. So you have, if you look at this carefully, you have 2 points at which, if you go around the loop, well, your loop gain is negative of what you see when you go around the loop. If you apply a sinusoid at this frequency or at this frequency, you have something that goes in. If you break the loop, it will come back in phase and larger. And yet, if you close this loop, according to this, it should be stable, which is exactly what we saw in that example we did last time, right? So that's why you need more advanced stability criteria. That pathological example, which is not that pathological really, but it is kind of like a strange thing. The reason for it shows why you need something more sophisticated. Now, the way actually this evolved historically was very interesting. They actually saw that they had systems that they had unstable systems. And when they increase the loop gain, so initially the system that you saw is that, okay, you have more, you increase the feedback, it becomes more kind of like underdamped, at some point it starts oscillating, right? But then they had some systems that as they increased the feedback, the system became stable. And it really confused the heck out of them. They said, what the heck is happening? Right? And then that was when Nyquist went and developed this criteria. So, well, okay, let's look at it systematic. So they actually observed this in practice first. And it didn't make sense to them. And then when they looked at it more carefully, they noticed this. So what happens from a Nyquist plot perspective, right? So you have, let's say you have a system that has a phase like this. So let's say this is your point -1, right? And then you go and do this. Right? So this is your original plot of the T of S. Right? So is it stable or unstable? Unstable, right? Because you're encircling the point -1. Now, if I increase the gain of this thing, or increase the feedback, let's say I do it in a scalar fashion, everything scales up. This becomes a bigger plot, right? So this becomes like this. It's a bigger version of that, supposedly. Now it became stable. These things they call conditionally stable. So this is a kind of special kind of stability. It's not. Now, why is it a special kind of stability? If you're designing that something that's stable like this, you have to be very careful. Because if your gain drops for whatever reason, let's say you have a nonlinear system or something like that. If your gain drops, then it becomes a challenge, right? It becomes a problem. So, because then it compresses, and then you can become unstable. And we'll talk about nonlinear. So it's not clear what happens when you have nonlinearity in the system. It's not clear what you get in those scenarios. So that's basically an example of kind of Nyquist criterion, right? And if I look at these plots, you can also see what gain and phase margin are, right? I mean, we haven't explicitly talked about them, and we'll talk about them in a short while. But you can actually define gain and phase margin, but you can see that if you just blindly look at the gain and phase at a certain point. So if you were to define gain and phase margin only here, there, you would not be able to differentiate between. So what is the phase and gain margin of this plot, for example? We haven't defined them formally, but if you look at it, if you just look at, say, well, wait a second, this thing here goes under negative 1 AD. So if you define it across the entire range, then you say, well, this has negative phase margin. But it's still stable, according to that definition. You could say, I'm defining phase margin only at this point. I don't care what happens before that. If my phase is less than negative 1 AD or above negative 1 AD, then I'm stable. You could define it that way, but then you will not be able to differentiate between different things. And so it's important to understand these plots and this behavior before you go and just blindly look at the phase margin and the gain margin. That we'll talk about in more detail. But it's important to understand the bigger picture. So this is the linear picture. The next thing we'll do, let's take a break, and then we'll come back and talk about the nonlinear view of this thing. What happens if the system is nonlinear? Okay? Any questions?
Do you get anything useful out of the Bode plots of the open loop and closed loop that we're not getting from?
Oh, okay. That's a great question. So the question is that do you get something useful out of the Bode plots of open loop and closed loop? And I'll talk about this a little bit more. But if you look at the Bode plot of the closed loop, right? We saw in that example actually that we did last time that even when it was unstable, the Bode plot of the closed loop didn't look horrible. It looked like something like that. And the system was entirely unstable because you're talking about two different quantities. And we'll talk about this next in more details. But it can be actually misleading if you just look at that. The Bode plot of the open loop is in fact very useful because the Bode plot of the open loop is this. This is the Bode plot of the open loop. Right? Just plot it in the polar coordinates, right? The loop gain is if you close the loop. When you say, oh, open loop, you mean open loop of just the amplifier. Yeah. Okay. Sometimes you look at so what you should really look at, even in this picture, right, is the Bode plot of the AF. Right? But sometimes people say, especially in the case of op-amps, people say the worst case scenario is if I have a feedback of 1. Assuming that you don't have active feedback, say the maximum feedback I can apply is that a wire that shorts the output to one of the inputs, right? To the negative. That's unity feedback. And you say, well, since that's the maximum amount of feedback I can evaluate, then in that scenario, this T of S becomes A of S. And that's why a lot of times you see sometimes, especially in the case of op-amps, people look at the open loop of A of S. But you have to realize that's a special case. Assuming that you are going to go to unity feedback. A lot of times you may not want to go to unity feedback. You may go to actually less than unity feedback, and then you may be over-designing. Because you may try to stabilize something that's stable for unity feedback, but if you have no intention of ever using it in unity feedback, or you know exactly how you're going to be using it, you can do that, but it's an overkill. You're compromising something else somewhere else. to achieve that. So that's a good question. Yes, very good. There was another question? Yeah.
Yeah, I'm a little confused about the stability culture.
Sorry? Okay, go ahead.
If 1 plus loop gain is the denominator of the transfer function, then wouldn't we want to look at the zeros of 1 plus loop gain?
Yes, exactly. That's exactly what we're doing, right? We're looking at zeros of that because we said it doesn't have any right half-plane poles because if the original loop gain didn't have any right half-plane poles. So we are just evaluating, so we are saying that this is 0 anyway if you start with a loop gain, that a loop that opened is stable. So this is 0. So the only thing we are looking at is the number of zeros, which is equal to the number of encirclements.
Well, why do we care about the right poles of the loop gain?
Why do we care about the, no, I mean, what it does is that if the number of right half-plane poles of the loop gain is 0, basically the open loop, it allows us to use this criterion this way. If you already have right half-plane poles, what this criterion gives you, the number of encirclements, is the number of right half-plane poles of the closed loop system minus the number of right half-plane poles of the original system, of the original loop, open loop loop gain. Right? Very good. Any other questions? All right.